Dice throwing tables. All right, well, let's roll some dice. And in particular, we'll grab this code here, copy it, and go here and paste it. Okay, and I'm going to grab this URL to show you what we're actually doing by going to that URL. And you'll see statistical tables for dice rolling. Okay, and so maybe I can do this. That's probably better. All right, so what this does is it lets you specify how many dice you have. Say we have 2 dice and number of sides. And we can create. And 2 6-sided dice. The smallest roll you can possibly get is a 2. The largest roll you can possibly get is a 12. It's double 6s. And here's your chance to roll exactly these different combinations. Now, of course, this is just computing this mathematically. There is direct mathematical way to do this. And, for 6 dice, it's really not that complicated. For 2 dice, it's not that complicated. But what if I had like 5 7-sided dice? Frankly, for anyone with a little bit of a math, particularly a probability background, still pretty easy. But yet, I would say that the average person might not be able to compute that's 4.9% chance of rolling a 15 with 5 7-sided dice. So we're going to give you a different way to go about computing these, and that is with Monte Carlo methods. So what we're going to do is first, we're going to have a helper method, then a helper function that lets us roll 1 die with a given number of sides, which naturally is just a random integer between 1 and that number of sides. And now the odds for a given number of dice and a given number of sides to roll this total, that's the problem that we're computing. So I want to roll like a 15 with 5 dice that have 7 sides each. And then you have to specify the number of trials, noting that the more trials you use, the more accurate a solution you're going to get. Fine. This here is a template for many Monte Carlo kind of problems. You have some number of successes. You run a whole bunch of trials. If your trial succeeds, you add 1 to your successes, and then the odds of success is simply the ratio of your successes to your trials. This 1.0 is actually a remnant from Python 2, not needed in Python 3 since division in Python 3 returns floats, not integers. In any case, so the question is, what constitutes a trial succeeding? Well, that's where you customize this particular kind of Monte Carlo approach for your problem. So this template is one that you'll see over and over again. You go into the trial succeeds, and in this case, trial succeeds means we're going to roll 1 trial, which is to roll that many dice with that many sides and see if you get the total that you're aiming for. So you have a total, you roll that many dice, you roll that 1 die, you add it into the total, and then we return that the total is the one we're looking for. So a trial succeeds is a Boolean, true or false, depending on whether or not the thing you're measuring actually occurred in the one time that you tried it. Out here is where you try it over and over again. So be sure you understand the difference between this for loop, which is rolling the dice repeatedly for 1 trial, and this for loop, which is running trial after trial. Okay? That's everything we need here. So then we print all the dice odds for given dice and sides, and for that, you go ahead and you run from dice to dice times sides plus 1. Why? Well, if I have like 2 dice, the smallest number I could possibly get is 1, 1, which is 2. The largest I could get would be, say, 2 6-sided dice would be 2 6s, which is 2 times 6. But since ranges are non-inclusive, you add 1. Okay? And then inside here, we'll go ahead and compute the results for different size trials. So just as before, we increase our trials by powers of 10, and then we compute the dice odds for that number of trials. And when we run this, what we see is trials, 10, 100, 1,000, and here's 3, 4, 5, 6, 7, 8, 9, and what are we doing here? It's dice sides in total, and print all odds. Oh, for 3 and 3. So we are doing 3 dice with 3 sides. Those are pretty funky dice. Let's go back here and see if we can run 3 dice, 3 sides. And here are the results that we're hoping to get. And here are the results that we actually got. Okay, so let's go back here. And for instance, 3.7% and then 11.1%. And we got 3.7%, 11.3%. So by 10,000 trials, we're beginning to converge pretty smartly on the final answer. However, say like at 1,000, not terrible, not great. At 100, pretty terrible. And of course at 10, just awful. So we definitely needed thousands, tens of thousands of trials in order to have pretty decent accuracy. But you don't need tens of millions of trials, and not, at least for not by 3 dice with 3 sides. The more dice, the more sides, the more different possible solutions or outcomes. Certainly the more trials you're going to need in order to get accuracy. Okay, so that would be that, except there's something very wasteful about this particular approach. And that is when we are seeing the odds of, say, getting a, so what do we got here? For K and Wonder range, trials, for the total. When we say, I want to test for every total, and we call dice odds for each total. See, that's wasteful because each time you roll this many dice with that many sides, you're going to get some total, which not only means you got that total, but you didn't get the other totals. So we could actually, instead of doing this over and over again, do it only once for all the possible totals. Think about it this way. I have 2 dice with 6 sides. It's a pretty traditional setting. And I want to know what are the odds for all the possible rolls. 2, 3, 4, 5, 6, up to 12. So I say, all right, I'll start with 2. And I roll the dice 100 times. And I get 3 2s. I don't know. So then I say the odds are 3%. But now I want to say, what are the odds of getting a 3? And I'm going to roll the dice another 100 times. But that doesn't make sense. I already rolled it 100 times, and I could have counted the 3s in the same time I was counting the 2s. That's the point. You only have to actually roll the dice for one set of trials, not one set of trials for each total. And that brings us to better dice throwing, which does exactly that. So I'll copy this, and I'll go back here, and I'll paste it in here. And so what better dice throwing does is it keeps track of our successes in a list for every possible total. And then when we get a total, we just add it to the successes for that total. Now the odds are a list of counts over trials. Once again, that 1.0 is a holdover from Python 2. And for each count in our successes, so successes being the list of successes. So that means that we get to do this once for all the possible counts. And now when we run this, it's going to be much faster than having to do it repeatedly for every single count. And that is our better dice throwing, and that's the dice throwing example.